Welcome to the Chem 1A pre-lab lecture for Experiment 5, Percent Water in a Hydrate. The objective today is to understand the nature of hydrates and to learn how to name them and write their molecular formulae. We will also learn how to calculate the percent water from a molecular formula of a hydrate, and also to determine the molecular formula of a hydrate based on its percent water content. In the experimental, we will learn to properly and safely use a Bunsen burner and a crucible, and we will learn the technique of heating to constant weight. Once we've collected our data, we will practice error calculations and review the different types and sources of error. The experimental objective is to determine the percent water of an unknown hydrate, and then to identify that hydrate from a list of knowns. You will then confirm the identity of the hydrate with your lab instructor and calculate the absolute and percent error of your experiment. So to begin, let's examine what exactly a hydrate is. A hydrate is an ionic salt that contains water molecules within its crystalline structure. What this means is that there's going to be a fixed ratio of water molecules to salt ions. Just as in a calcium carbonate salt, we have one calcium ion to one carbonate ion. In calcium carbonate hexahydrate, we have that one calcium ion, one carbonate ion, and 6 waters. You will note that I use the Greek prefix hexa to indicate 6 waters. When naming hydrates, we use these Greek prefixes to indicate the ratio of water to salt. Another example would be sodium sulfate decahydrate, deca for 10, or manganese sulfate monohydrate, mono meaning 1. When the water is removed from these hydrates, they are called anhydrous salts, meaning do not contain water. An example of what this might look like is given here, where the hydrate, cobalt chloride hexahydrate, has a lovely fuchsia color. And if the water is removed by evaporation, we have the anhydrous salt, cobalt chloride, which is a deep blue color. Not every hydrate loses its color or changes its color upon becoming anhydrous. However, it is a good sign that all of the water has been removed if we do see this color change. Percent water is a mass ratio, and it is calculated by dividing the mass of the water by the mass of the hydrate. In order to determine the percent water from a molecular formula, we can begin by assuming we have 1 mole of our hydrate of interest. Let's work through the example with calcium chloride dihydrate. We can begin by determining the molecular mass of the entire molecule. So we are including 40.78 grams for our calcium. We have 2 chloride ions, so 2 multiplied by 35.453 grams for the chlorides. And then we include the mass of the water, so 2 waters, and each water weighing 2 hydrogens, so 2 times 1.097 grams for the hydrogens, and 1 oxygen, so adding 15.999 grams. If we do the mathematics on that, we'll find that the molecular weight of calcium carbonate dihydrate is 147.021 grams. We next find the mass of the water alone, and we can do that by simply isolating this last part of our calculation. So 2 waters, so 2 times 2 hydrogens plus 1 oxygen, gives the mass of water as 36.037 grams. We now take the ratio of the molecular weight of the water over the molecular weight of the hydrate and multiply by 100 to give an expression in percent. 36.037 divided by 147.021 times 100% yields 24.511%. Therefore, calcium chloride dihydrate is 24.511% water by mass. In your experiment today, you will be determining the percent water experimentally. You will do this using a Bunsen burner and a crucible to heat your hydrate. So let's begin by going over how to use a Bunsen burner. As you can see in the diagram here, a properly adjusted Bunsen burner will display two flames, an outer flame of blue and an inner blue flame. The hottest part of the flame is at the upper tip of the inner blue flame. To achieve this, begin by lighting your Bunsen burner. First, turn on the gas tap until you can hear a gentle hiss of the gas coming through the line. With your match at the ready, strike the match as soon as you hear the hiss, and then bring your match towards the tip of the Bunsen burner, moving horizontally, coming in from the side until the flame comes to life. We can then adjust the airflow to achieve a perfect dual flame by adjusting the air supply valve at the base of the Bunsen burner. Simply twist this valve until you can see a clear distinction between the inner blue flame and the outer blue flame. Once you have mastered lighting your Bunsen burner and achieving the double blue flame, we can move on to the setup for the experiment. Your hydrate will be heated inside a crucible using your Bunsen burner. Begin by assembling a support system for your crucible. Your crucible will need a support system so that it can be held safely above the flame. Assemble an iron ring and a clay triangle as shown on my left here. Begin by attaching an iron ring to your ring stand, and then place a clay triangle atop of it. The clay triangle is perfectly sized to hold your crucible safely. You will then need to clean your crucible well using steel wool to remove any residues. You can then use a damp paper towel to remove any dust. Next, you will place your crucible atop the clay triangle and gently heat it with the outer blue flame to drive off any moisture from the damp paper towel and any other residues that remain on the outer surface of the crucible. It is important to allow the crucible to fully cool before you go and get its empty mass. Hot objects appear to weigh less when we weigh them because warm air currents surrounding the object gently lift it up, causing it to appear to have less mass on the balance. Once you have cleaned your crucible, dried it, cooled it, and weighed it, you can now add your hydrate. When you are heating your hydrate, it is very important to keep the crucible lid ajar. In the process of this experiment, we are beginning with a hydrated salt and then heating it to evaporate the water. So we will need a place for the water vapor to escape. You do want to still have the lid on the crucible, however, to avoid your sample from overheating and popping out of the crucible. So it's important to have the lid on, but with allowing a small gap for the water vapor to escape. When heating your crucible with the Bunsen burner, it's important to keep the flame moving around all the surfaces of the crucible. This will ensure even heating of your sample within the crucible, and also avoid burning of the crucible, which can occur if you allow the flame to stay in one spot for too long. It is important to remember never to touch the crucible with your fingers. Not only may it be hot and burn your fingers, but your fingers contain oils and proteins that can easily be transferred onto the crucible, and this would cause an increase in mass. Instead, you are provided with crucible tongs, and you can use them to handle the crucible like is shown in the diagram on this slide. Once again, I want to remind you to allow your crucible to fully cool before measuring its mass. Whether you choose to measure the mass of the crucible with or without its lid is not important, so long as you are consistent in each time that you weigh it. If at the start of the experiment you included the lid, then continue to include the lid throughout. It's also a good idea to always use the same balance throughout your experiment. There's a template on Blackboard for you to use to record and analyze your data. This data will be used to identify your unknown hydrate. Begin by calculating the percent water from the starting mass of your hydrate and the mass of the water lost, so that percent water is equal to the ratio of water lost divided by grams of sample times 100%. Based on the percent water, compare these to the hydrates that you looked at in your pre-lab and propose the identity of your unknown. Then calculate the absolute and percent error based on this proposal. Next, check with your lab instructor for the true identity of the hydrate. If it's the same as what you proposed, your job is done. However, if it is different, calculate the absolute and percent error to compare your data to the true hydrate. Here's an example of how you would calculate your percent water from your data. I'll use Microsoft Excel to assist with my calculations. Here I have entered the raw data from my experiment. You will see the mass of my crucible unit after cleaning and heating, then the mass of the crucible unit with a hydrate added. You'll see that it's a difference of about 0.5 grams, as indicated by the lab manual procedure. Next is the mass of my crucible and hydrate after the first heating, and then after the second heating. And you'll see that there's just a small difference in the last decimal place, and so I can conclude that I have achieved constant weight. To calculate the mass of my hydrate, I would simply subtract the mass of the crucible from the mass of the crucible and the hydrate. So, mass of the crucible and the hydrate minus mass of the crucible. My hydrate weighs 0.6425 grams. Now, to determine the amount of water that was lost due to heating, I can subtract the mass of my anhydrous form from my hydrate. So mass of crucible with hydrate minus mass of crucible with anhydrous salt, so second heating, gives me a mass of 0.130 grams. To calculate the percent water of my hydrate, I simply divide the mass of water by the mass of hydrate and multiply by 100 to give a percentage. So I can conclude that my hydrate is 2.02% water. I would then repeat this process 2 more times and get the average percent water. There are a number of reasons why the percent water that you found experimentally does not match that which your instructor tells you is the known value for percent water of your unknown hydrate. I'll get into these reasons shortly, but first let's see how to calculate and express error in terms of absolute error, accuracy, and precision. Absolute error is how much you were off by. It's simply the difference between your experimental value and the known value. We subtract the known value from the experimental value so that if our experimental value was high, we will end up with a positive number. On the other hand, if our experimental value was low, we will end up with a negative number. Absolute error has a positive and a negative expression, and this is important to remember. From absolute error, we can calculate accuracy. Accuracy is a measure of error that takes into account the magnitude of the known value. Simply stating that you are off by 10 grams doesn't really tell you how close you were to the true value. If the object was supposed to be 1 kilogram, being off by 10 grams isn't so bad. However, if the object was only supposed to weigh 5 grams and you're off by 10 grams, well, that's a much larger deal. So percent error gives an idea of the absolute error in terms of the magnitude. To calculate accuracy, simply take your absolute error, including its positive or negative expression, and divide it by the known value and multiply by 100%. Percent error is used synonymously with accuracy. Lastly, precision gives us an idea of how reproducible your measurements were. You will be doing 3 measurements to determine the percent water in your hydrate. However, other class members may have the same unknown hydrate as you do, and you can include their measurements as well in your precision calculation. Precision looks at the wobble room between measurements, and it is expressed as a positive or negative value at the same time. This means precision gives a range higher and lower than your reported average value in which the measurements can vary. Precision is calculated as the square root of the sum of each value minus the average squared, divided by the number of values minus 1. You will apply these calculations to your own data as well as to the class data. So in discussing error, we can broadly categorize it into two types. First is systematic error. Systematic error is directional. This means that systematic sources of error will always cause a measurement to be either high or always cause it to be low compared to the known value, and they are consistent throughout the experiment. One example would be not calibrating a balance. If you did not first zero the balance and it already had a mass in the databanks of the scale, then you will always be off by that same amount of mass. Similarly, if your graduated cylinder was poorly calibrated so that the gradations are larger than they need to be, every time you measure using that graduated cylinder, your values will be lower than they should have been. These are systematic types of error. Systematic errors do not appear in standard deviation since they are the same in every trial, but you will see a difference in terms of accuracy of your measurement. The other type of experimental error is random error. Random error is not directional. As we can presume from the word random, the errors cause both positive and negative differences in the measured value. Random error will often appear as a large standard deviation, so a large range in the number of values around an average. If the random error is truly random, it will not be visible in the accuracy. You may get the exact percent water that your unknown should contain, but your standard deviation or precision could be quite large. Random errors often occur through an inconsistent sample, meaning a heterogeneous sample that was not mixed well, or from poor technique. So whenever we perform an experiment, it's very important to acknowledge that there are sources of error, and that only by acknowledging these sources of error can we control for them. In general, sources of error include equipment error, which reflects the limitations and calibration of a piece of equipment. How many decimal places does it go down to? If you are using a pan balance, you're going to have a greater source of error than if you're using an analytical balance, which gives greater precision. Another source of error is the method. This means, how did you go about doing the experiment? Did you choose equipment and supplies that will fit the objective and give the highest amount of precision possible? Did you choose to use an analytical balance rather than the pan balance? Did you choose a sample that is stable or one that is going to evaporate on you or absorb water, meaning a hygroscopic sample? These considerations need to be taken into account when designing an experiment. Another source of error could be the sample itself. As I mentioned in random error, an inconsistent sample can lead to a large standard deviation. Other problems with sample could be their volatility, as I mentioned, if they evaporate, or if they absorb water, or if they are simply not pure. The reliability and consistency of your sample throughout the experiment is definitely something to consider when designing your hypothesis. We are all human beings, and so we all make the odd mistake now and then. These everyday errors of spilling the sample, sneezing into our beaker, overshooting our titration, are not inherent in the experiment, but are basically human error, and we call these types of errors technique errors. A last source of error is context. This comes from not fully reporting your objective and what your findings are. What are you measuring? And how did you measure it? Are you clearly describing what you want to know? For instance, if you are describing the size of a football and you simply tell me that it is 30 centimeters, is this the length? Is this the circumference? Is this the vertical diameter? It's important to always be clear when you are describing a measurement. In specific, there are several sources of error that come from experiment 5. The method error could be involved in not heating to constant weight, so insufficient heating of the sample. Insufficient heating of the sample would be a systematic error, since not heating to constant weight will always give us a lower percent hydrate, lower percent water in our hydrate than if we did heat to constant weight. On the other hand, overheating of the sample, allowing some of the sample to pop out, would also be systematic or could be random if it doesn't happen every time. Another method error would be taking too much time to get to the balance before weighing your sample. All hydrates attract water. That is why they are hydrates. And so if we leave an anhydrous salt out in the air for too long, it will begin to gather water molecules back into itself, thereby increasing its mass. Sample error comes from how your hydrate was presented to you at the beginning of this lab. Perhaps it was overly wet, or a little bit dehydrated already. Perhaps your sample was not pure and contaminated with either a little bit of the anhydrous form of the salt or another salt entirely. Perhaps your sample is not a homogeneous mixture. Equipment error that comes from experiment 5 is going to be based on the balance that you use. Recall that it's best to use an analytical balance since we are looking at very small mass changes. Also, try to use the same analytical balance throughout the experiment to account for any variations from balance to balance. Technique error are things that we can try to avoid, and you should do your best to avoid them. Keep your crucible lid on whenever you are not heating the sample. This will prevent foreign material from dropping into the crucible, such as dust or a hair. Again, make sure you do keep the crucible lid on but slightly ajar while it is heating, so that no sample will pop out of the crucible. Remember to always move your Bunsen burner flame around the crucible to prevent it becoming overheating and oxidizing. Also, never touch the crucible with your fingers after you've begun the experiment. Always handle your crucible with tongs and place it on a clean paper towel or in an evaporating dish to cool. Lastly, remember that when you're using the analytical balance, it's important to close all 3 of the glass doors before recording the measured mass. Alright, so hopefully at this point you have a good understanding about what's going to be happening in today's lab. I just want to leave you with some few safety considerations before you head off to your experiment. So in addition to your lab coat and goggles, this time please remember to really leave your hair tied up well. Specifically because with Bunsen burners, one, we never want to leave them lit and unattended. So if you are heating a sample and you need your partner to go weigh something, your partner can weigh it without you. You stay with the flame. And then, as I mentioned, make sure your hair is tied well back. So if you have really long hair, simply putting it in a ponytail is not enough because that ponytail can fall forward into the flame. So put it up into a bun or pigtails or whatever you need to do to keep sure that your hair stays behind your face. Also, it's a good idea to keep your bench tidy and not to have random bits of paper that could combust lying around, such as paper towels and loose paper. If there is an emergency and things start catching on fire, first thing you should do is turn off your gas tap and then call over your instructor and they will help you and put out the fire and make sure that everyone remains safe. Okay? Well, have fun and good luck.